Hi, my name is Jeremy Blackstone,
And I'm Brian Searle.
and today we're going to present on the paper Active Hardware Metering for Intellectual Property Protection and Security.
So, the problem that this paper is discussing is the fact that intellectual property is stole often by these fabrication foundries when they send the chips to get fabricated. And this is happening more often because most IC design companies these days are fabless, so they have to outsource it, and it's cheaper, so it makes more sense for them in a business sense. But by releasing these IC designs, test patterns, and test responses to the foundries, it is a huge risk for having this happen. The fabrication is able to make these copies because they already have these masks and are just able to print out more for cheaply, didn't have to go through any design cost. And IP theft, it's often said by people that it's a victimless crime, but this 2013 IP Commission reported that over $300 billion were lost from IP theft in America. This is just America, and this is happening worldwide. So other countries have to deal with this as well, and it is a big effect because those are a lot of jobs that are potentially lost. And it's even reported that over 70% of this is actually happening in China, which is amazing. That's all. A lot of it's in one place.
So, both hardware and software piracy result in security threats, financial loss, and negative economic impacts. However, integrated circuits or ICs are used in almost all electronic devices, making the potential consequences even more pervasive. Hardware tampering and piracy is also a more difficult problem to address. In many cases, hardware adversaries have full access to the structural specification of a hardware design. They have full access to manufacturing test vectors, and a lot of time they have considerable economic resources and technical expertise. Some of them are even funded by governments. Furthermore, there are many strategies to launch IC tampering attacks, and not much is known about how to prevent them. So, in the normal fabrication process, Alice, the legitimate owner, makes her IP available to Bob, the fabrication house. So Alice pays for X ICs implementing the design of her intellectual property or IP, and Bob uses that IP to construct a mask. That mask is used to implement the design. So Bob uses the mask to make X copies of the design for Alice to complete their business transaction, but he also makes Y copies of the design for himself without Alice's knowledge. So now Bob can sell these Y illegal copies of the design for a profit.
So the real obvious approach is this split work that I call it, where they would send different layers of the IC to different foundries. So the foundries don't have a fully working IC, the end product. Uh, and it seems like a real quick fix, each fabrication does this process, this layer, that layer. However, there is a big problem with this, even though it seems like it would be real effective, is that the fact that it's real expensive to split it up. And not only that, these fabrications won't be able to perform a full test on the put together IC. They would be doing individual parts, so it would actually end up having a lower production yield, higher costs, and it would require more improvements, and there's just a lot more potential for errors along the way that it's just not worth it. So before we get into active metering, I want to discuss this passive metering, which was released before active metering, and it's a good starting point. So the goal of active metering is to be able to determine the existence of counterfeits and even quantify those counterfeits on the market. So it's able to do this by having a small configuration that it's programmable, or it's able to be loaded onto the board somehow. And the real important part is that it results in different configurations for the chip. So even though they have different configurations, they will actually result in the same. So these configurations can result in different things. They can be in a synthesis process even, so it could be our own chip, and they could laser off states, or it just has to result in something different. This register assignment is often used, and even a few registers can result in using the registers differently results in a high number of different configurations. And then since these unique configurations result in different, they're able to use it as an ID almost, and this ID needs to be provided to the IP owner, and they will store this ID on their database. And then doing a small sample set test of potential counterfeits on the market, they are able to use statistics and calculate the probability or approximate and detect, not only detect those counterfeits, but they're also able to approximate the number of them that are on the market, which is pretty crucial just off a small set of counterfeits. So now that we went over past metering, I want to go. This is the active metering approach that's taken by this paper. There are multiple active metering approaches that have been done today, but this paper claims to be the very first one. So there are more advanced versions of this today. But the goal of active metering is to prevent ICs from working right when they're fabricated. So once they're fabricated, the chip doesn't work properly. So the fabrication has these chips that don't work fully. And then the IP owner needs to require a key to activate it, and then that will put it into the fully functional mode. So this is able to fight IP piracy by reintroducing the IP owner into this fabrication process, and they can do it remotely. And so this really requires these random unique blocks they use to generate IDs in this paper. And they also use finite state machines to prevent transitions to fully functional states unless the chip has been activated. So this is the scheme that this paper takes. It requires a FSM or finite state machine, a fully operational, needs to be on the chip, and then they're able to add these are the black states, these are the finite state machines, the operation, we'll call them the operational mode. And then they need to extend them with these BFSM or boosted finite state machines. And these red ones, the boosted finite state machines, are the spots that do not allow fully operational mode unless the key is required. So if they have the correct key activation, they're able to transition from example 5, 6, 7, and then transition to the reset state or the starting state of the finite state machine, which allows the full operation, which is the end state, the goal. So using these random unique blocks, these RUB, they generate an ID, and those IDs correlate to the state in which it will start in. So they need to be remotely stable and get into these BFM states on startup. And that requires a specific number of them. So they will have, the RUB, the size of the RUB required, and that correlates to how many states are needed. And they need to be able to generate a guarantee that it will start in one of these BFSM states. That needs to happen. So this is the manufacturing process, that the whole process. I want to first go over passive metering so you could see the difference in the scheme. The passive metering, or Alice, the IP owner, will provide the manufacturing specs to Bob, the fab, and then fab will manufacture it, he will test it. Once he detects the chip's working, he'll put it to market. And then passive metering is then on the market able to detect counterfeits and then approximate how many are on the market. However, that doesn't prevent Bob from making more. And this is where key activation metering process changes. It adds in right here this key calculation, which is reintroducing Alice, the IP owner. So this happens by Bob having to require the flip-flops, the states that the RUB generates. So once these states are read out, Alice is able to calculate That's the reintroduction of Alice.
So all the way through, the global flow basically begins with Alice taking the high-level design description and synthesizing it to get a finite state machine. Afterwards, a boosted finite state machine, or BFSM, is created by adding additional states, so there are multiple transitions that could possibly lead to the reset state. The detailed design specifications are then sent to the fabrication house to manufacture the ICs. When the manufacturing process is complete, the fabrication house is able to scan and read the flip-flops, but is not able to find the sequence of inputs required for the correct transition from the initial added state to the reset state in order to unlock the IC. So the fabrication house has to read out the values and flip-flops of each IC, send them back to Alice, and then Alice uses these values along with her knowledge about the original state transition graph to compute a specific key, which she gives back to the fabrication house to unlock and activate the IC. So, one of the most important aspects of active metering is variability based ID generation. So, one method for variability based ID generation mentioned in the paper involves changing the threshold of circuits utilizing the impurity of random dopant atoms. Another method attempts to implement random IDs on polycrystalline silicon thin film transistors. Unfortunately, both of these methods can easily be detected and they require specialized process technology. In order to avoid this, the active metering scheme presented in the paper utilizes a method that uses threshold matches between two NOR gates that positively feed back to each other. There are other ways for variability based ID generation to be done, such as physically unclonable functions. However, for the context of the paper, the only thing that's really needed for active metering is generating a stable unique ID. So there are a number of attacks that can be done against an active metering scheme. However, just to go over a few, the brute force attack is where Bob systematically applies input sequences to the BFSM. So he can randomly select input sequences, and his goal is to discover the correct input sequence so he can reach the reset state. In a reverse engineering attack, Bob scans the flip-flops in order to try to extract the original state's transition graph. The goal here is for him to remove the state transition graph from the BFSM in order to separate the original states from the added states. Thirdly, combinational redundancy removal attempts to remove combinational logic not necessary for the behavior of the circuit. So once again, so it attempts to find the set of reachable states in the finite state machine. Again, the goal here is to remove states added for the BFSM. So some countermeasures that the paper proposes are black hole FSMs merging the functional BFSM with other FSMs and using large circuits. So black holes are states that make exit impossible regardless of the used input sequence, as you can see with the H states here in the diagram here. So this can defend against both brute force and reverse engineering attacks because after a limited number of key attempts, they'll just completely brick the IC. So regardless of the input sequence that Bob uses, it's impossible to unlock the IC. So merging functional FSM with other FSMs basically involves Alice co-synthesizing her BFSM with tests, debugging, authentication, or any other FSMs she has available in order to make it more intricate and make identification of the functional FSM more difficult. This also defends against brute force and reverse engineering attacks because by making the BFSM even more intricate, it requires even more input sequences for Bob to try in order to get the original FSM. Large circuits are effective against combinational redundancy removal because that attack is only possible for relatively small circuits, even when implicit enumeration techniques are used. So as long as the circuit that Alice designs is large enough, combinational redundancy removal isn't a viable option.
So even though this is the first active metering approach, there are other schemes now that will use, modern cryptography for remote, try to do more security in that reintroduction of Alice. But that is the key to this whole thing, is that by reintroducing the IP owner into the fabrication process, they're able to make these chips useless. So if they spit out extra copies, then those chips are just bricks, basically. And then this is done by the key exchange mechanism. One of the cool things about this that I just wanted to mention, though, is this remote disabling that they're able to do, and it's innate to the way that this whole scheme is set up. Since they have these finite state machines, they're able to use these black holes, which was previously mentioned. but they can add it into the operational mode. So you could see in Q2 it can jump into H1. So that means that if as long as Alice is able to remotely check the configurations and determine if the state was accessed illegally or if it was like attacked, if it's a fake, they don't have the ID in their database, something. At any point, the IP owner will be able to just disable the chip and brick it. So even if an attack is successful, the IP owner could then make the chip useless. So thanks for listening. That is our active metering video.